Now let's calculate the change of internal energy from 3 to 2, and then we'll find the change of the availability. So U3 minus U2 is mc sub A T3 minus T2 is equal to 0.0071 times 0.7176 times 3253 minus 689, where I have this is equal to 13.82, in that the availability A3 minus A2 is equal to 13.82 minus 2.51, where I have the availability is equal to 11.31. And we have the Q in is delta U, so it's 13.82. Now let's make kilojoules, right? So anyway, so now let's make sense of these numbers. So this represents Q in. So Q in, when we put heat into this, where did it go? It went into two things. It went into producing work or in heat leaving. So I have W net, actually in this case, the W is slightly greater, so I have W net and Q out. So that's where it went. Of the heat out, so Q out is 6 kilojoules. So it's the heat in minus the work. Of that, of this 6 kilojoules, there's a work potential of 3.5 kilojoules. So in an engine, so what this means in an engine, so if I translate this from this, so the work potential that we recall from chapter 9 had to do with the energies of potential to do work. So what we have is then the heat out, which models exhaust, has a high work potential associated with it. So one of the things we're looking at eventually on real engines is how we can make use of this work potential. So it tells us here that there's a work potential that's not being used in this cycle. Perhaps we can use it later on, and we'll see. And when we look at this, so if we look at the availability, so we know the heat in Q in had a work potential of 11.31 kilojoules. So of the 13.82 kilojoules of heat in, this was the work potential. How much got converted into work? 7.8. And so that gives us an idea of what's going on with the work potential and how well it's being utilized. And so this was an air standard cycle which modeled the spark ignition engine. We can do the same air standard type analysis for a diesel engine. And so we have an air standard diesel cycle that we'll look at now. And in this, we're characterizing it slightly different. We're again using air replaces air fuel. We're having heat in for combustion. And the process is going to be constant pressure. In the Otto cycle, it was constant volume. Here it will be constant pressure. The heat out will be the exhaust. And that will be a constant volume, just as it was in the Otto cycle. And we'll have isentropic compression and expansion. So if I look at that now, let's draw the air standard diesel cycle and see what it looks like. And then we'll do a problem with this. Well, let me draw it and then I'll talk about it. So if I look at this on a PV diagram, and so now I'm going to start at bottom dead center, top dead center. What happens in diesel cycles is that the compression is greater, the compression ratio is greater because I need a high temperature at state 2 when we inject the fuel into it. So now I'm going to have a higher compression from 1 to 2. So I'm going to have a higher compression ratio, and now I'm going to add heat at constant pressure. So here's the PQN. And then we expand in a reversible adiabatic fashion down to state 4. So we have 1, 2, 3, 4, and then we have Q out. And the TS diagram looks similar to the one for the Otto cycle. And the difference isn't something that we can see when we draw it by hand. There's a slight difference in a line of constant pressure on the TS diagram and a line of constant volume on the TS diagram. But it's not a symmetric cycle. So now let's look at example 13.3 and we'll go through that. And notice that this has the same amount of heat in. We're changing the compression ratio, but we're going to start the same and do a similar analysis that we did for the Otto cycle. And we'll just see how the pressures are different and the temperatures are different, particularly when we go up to this point. So example 13.3, you can read that T1 is equal to 300 degrees K, P1 100 degrees, 100 kPa, Qn is equal to 1840 kilojoules per kilogram, R is equal to 16. So rather than R being 8, R is 16. Now we'll go through it and find the various cycle state points. So V1 is RT1 over P1 is 0.287 times 300 over 100 is 0.861 cubic meters per kilogram. V2, V1 over V2 is equal to R. So V2 is equal to V1 over R is equal to 0.861 over 16 is equal to 0.0538 cubic meters per kilogram. And you see that the specific volume is smaller in the diesel cycle than compared to the air standard Otto cycle. And so now let's find T2. Same way, T2 is equal to T1 times V1 over V2 to the K minus 1. So this is equal to 300 times 16 to the 0.4. So T2 is equal to 909.4 degrees K. And in the Otto cycle, it was 689. So in the last problem, if you refer back, it was 689. And I can find the pressure, P2, is equal to P1 times V1 over V2 to the K is equal to 100 times 16 to the 1.4, or that P2 is equal to 4850.3 kPa. Now the process from 2 to 3 is heat in at constant pressure. So heat in at constant pressure is equal to the change of enthalpy. So Q in is equal to H3 minus H2, which is C sub P T3 minus T2. So we have 1840 is equal to C sub P 1.0047 times T3 minus T2, which is 909.4. Or we come up with that T3 is equal to 2740.8 degrees K. So, and now P3 is the same. So I found T3 from the heat in, but it's constant pressure. So P3 is the same, and I can use the ideal gas law to find specific volume 3. So P3 is the same as P2. Is equal to 4850.3 kPa. V3 is our T3 over P3, 0.287 times T3, 2740.8 divided by P3, 4850.3, and I get that V3 is 0.1622 cubic meters per kilogram.